Hello, everyone. Welcome to the last lecture of the course. We are discussing bipolar junction transistors, and we are talking about these amplifier circuits of the bipolar junction transistors. So, in this lecture today, in the last lecture, we started with these BJT amplifier different configurations, common emitter. We discussed two configurations, common emitter, and also kind of a more uh, um, detailed version of a common emitter with a common resistance as well. We modeled those models, find out the open circuit voltage gain. Again, there are four things that we need to find out: input resistance, output resistance, open circuit voltage gain of an amplifier with a low resistance, and the overall voltage gain. So I guess five things. And then we also did an example. So in the lecture today, we are going to talk about this common base configurations. Then one configuration is remaining, common collector. And after that, we're going to do one more example today, and that would be it. All right, so let's start with a common base configuration. If you look closely over here, in this common base configuration again, our base is common, right? So common base configuration. Okay, great. And now we have input voltage that is appearing over here, input resistance, looking into the emitter. So if we are looking into the emitter as an input resistance, so our base to emitter resistance will be the emitter resistance RE, right? So our input resistance will be RE. It's very simple case. Now we are going to use again, this is the T model. So if I go back and use the T model here, right? So we are using this alpha times IE and IE RE. Our RE equals VT over IE and alpha over GM. So we're going to use these equations again. Where's common? Okay, common base. So this is our input resistance, RE. And our output voltage is here. So resistance looking at the output terminal would be equals to R naught equals RC. So let's find out again all the values, how we solve the circuit, input resistance, output resistance. Then we find out the open circuit voltage gain of an amplifier, and the overall voltage gain. All right. So input resistance looking into emitter, right? So if we look at the circuit and look into the emitter terminal, the resistance that we're going to come across is the input resistance, since our base is grounded. So in this common base model, our base to emitter resistance is RE, or the emitter resistance. So we're going to come across RE. So this means that our input resistance is RE. And we know that RE equals alpha over GM. And since sometimes we assume that alpha is almost approaches to 1, so we can also write this thing as 1 over GM. The exact equation would be alpha over GM. Okay, great. So our input resistance is done. Our output resistance, as we just talked about, it's equals to the RC value. After this thing, the third thing that we find out is the overall voltage gain when load resistance is not connected, V naught over VI. So let's find this thing out. We know that our output voltage again is equals to, we're looking at the direction of the current. So it should be RC into our collector current, right? Minus this collector current, or minus IC minus IC is alpha times IE into RC. Now let's find out the input voltage. Our input voltage, if I look at this input voltage here, or this input voltage here, right? So this input voltage equals, our resistance is RE, and our current that is flowing through this branch is the emitter current, IE, right? And our resistance is RE or RN. So I can write, looking at the direction of the current again, minus IE into RN, or minus IE into small re. Now we know the value of what is the value of the RE? RE is alpha over GM. So it will be minus IE into alpha over GM. So I ended up finding the value of VI as well. So AV naught when no load resistor is connected, V naught over VI minus alpha IE RC minus IE alpha over GM. So minus alpha IE. So this will come out to be RC into GM. So AV naught open circuit voltage gain would be equals to GM into RC. Okay, great. So we ended up finding out the value of the open circuit voltage gain. What's the next thing that we want to do? We want to find out the voltage gain with the load resistor connected, and load resistor will be connected in parallel to RC. Okay. Now RL connected in parallel to RC. So once, if our RL is connected to RC, then this will simplify our analysis. Our voltage gain now, V naught over VI with RL connected, will be equals to GM RC in parallel with RL. Now we have a load resistance that is also connected. We did this analysis in detail while characterizing this amplifier over here, right? Going back to this thing. Oh, okay. Right, you didn't have an R naught here. So if you have a R naught also appearing, so it will be the two resistance will come out to be in parallel, and then your RC will come out to be in parallel with R naught. All right, so we did this. Where is the common emitter? I'm sorry, we are doing common base. All right. Okay. All right, yeah. So this is the overall voltage gain again. No, this is the voltage gain of an amplifier, not the overall voltage gain. Now we need to find out the voltage gain of an amplifier. So our voltage gain of an amplifier is, sorry, let me go back here. So even if you, for example, even if you are doing it from scratch and you don't want to go back to the basic analysis or the configuration analysis, if you will just assume that you have another resistance that is appearing over here, that all you need to do while finding out this V naught value, you're gonna see that this RL will appear in parallel to this, right? And if you will replace this thing over here, RC in parallel with RL, this parallel resistance is going to reflect over here with the load resistance attached. So that is why we have a parallel RC in parallel with RL with the voltage gain over here. Okay, now let's find out the value of the overall voltage gain. Overall voltage gain, we know that equals to VAV, the voltage gain of an amplifier, with input resistance plus signal resistance. All right, so this is equals to GM RC in parallel with RL, and then our input resistance. Our input resistance is, where's our input resistance here? Input resistance is RE here, and signal resistance is signal resistance. Okay, so RE over RE plus signal resistance or signal. All right, so we can write this thing as GM RE RC in parallel with RL over RE plus R signal. Now we can also replace this value. For example, we know that RE equals alpha over GM. So our GM into RE, this product would be equals to alpha. So if this product would be equals to alpha, then we are going to simplify this equation further with these values. So this will be the overall voltage gain of an amplifier. Our overall voltage gain of an amplifier will be alpha times RC in parallel with RL divided by RE plus the signal resistance. Okay, so this is our basic analysis of a common base configuration. Now we are going to do a common emitter configuration. This is a loss configuration for our analysis. We will do one more example and wrap up our lecture today. Okay, so I guess the slides are, so 89 slides should come after 87. And we probably need one more slide. So one thing that I'm going to do is, okay. Okay, so I am going to add one more slide here to do this analysis. And okay, now this should be good. Slideshow from current. Okay. Okay, great, right? So this was our common base. Now we have a common emitter. This again, this analysis is a common base analysis. I'm gonna wrap up the slides when I will upload the slides. I will put them in the right order. Okay, let's do the common collector analysis. Common collector analysis. Over here, this is our common collector terminal. Our output voltage is over here. Our resistance R naught is again looking into the output of the bipolar junction transistor over here, or looking at the output into the emitter terminal. And our input resistance will be looking into the base terminal, right? So we can also replace this circuit by this equivalent circuit. Our equivalent circuit over here is again this T model, where our emitter is represented by this resistance RE, and our collector terminal by this collector current control current source. Okay, so we are going to do exactly something very similar analysis over here. We're going to find out all of these values of the input resistance, output resistance, and all the gain values. So the first thing first, if you look closely over here, this branch, this emitter branch, it looks very closely to something that we did in the last lecture, when we had at the emitter terminal we had this resistance RE, and then we had another emitter resistance, capital RE. So our analysis is going to be very simple and helpful. So I'm not going to redo those equations. Where is that? Common emitter. Okay, right? So our emitter terminal looks very much the same like this. So you have a resistance RE, and then rather than this resistance, now you have a load resistance attached, RL. So this is, right? So this means that when you have a load resistance attached, so your input resistance looking into the base terminal will be equals to this value. And this is the equation that we derived in detail in the last lecture. So you're now our input resistance, first thing that we want to find out, right? So our emitter branch looks very similar to common emitter configuration with emitter resistance analysis, right? So we did this analysis and we find it out the value of the input resistance. Let's go back and see that value, right? So this was the value of the Rn that we were interested in here, and the value that we ended up finding was Re plus Re. These were the two resistances that were appearing in the emitter branch, and then into 1 plus beta. So similarly, we can say that our Rn would be 1 plus beta, and the two resistances that are appearing over here are Re plus Rl. So this will be our input resistance. Our output resistance looking into the emitter terminal would be more simpler, and our output resistance would be equals to small re. Okay, great. Now let's find out the value of okay, so let's find out the value of the open circuit voltage gain now, AV naught, when RL is not connected. Right, so we know that for example over here, since our so how we can find out the value of the open circuit voltage gain? Our open circuit voltage gain is when RL is infinite. So this means that our load resistance will be open circuited. If I am going to open circuit this load resistance, then my output will be equals to my input voltage, right? Then this voltage will become equals to this. So that is why my open circuit voltage gain over here is 1. Okay, now let's find out the voltage gain of an amplifier. The voltage gain of an amplifier, we know that from earlier analysis, it is AV naught over RL plus R naught. Over here, our output resistance equals Re. So our overall voltage gain would be equals to AV naught is 1. RL is, we have our resistance RL plus R naught is Re. So this is the overall, this is the voltage gain of this amplifier. Now we have to find the voltage gain, overall voltage gain, right? So the overall voltage gain of this configuration is going to be output voltage to the signal voltage multiplied. Okay, so this should be output voltage to the signal voltage is the overall voltage gain, right? So we can also write this thing as V naught over Vi multiplied by Vi over V signal, and this thing equals AV. So our voltage gain of an amplifier is, what is the value of AV? The value of the AV is RL over RL plus RE, RL over RL plus RE multiplied by Vi over V signal. So let's find out this value, Vi over V signal, right? So this can easily be found out by using this voltage divider rule over here. So our Vi would be equals to, right, so this is our Vi. So Vi will be equals to V signal, and that resistance again is appearing to the total input resistance plus signal resistance. So I'm going to write this thing down, RL plus RE into Vi over V6, or divide this by over here. You're going to left with Rn over Rn plus R signal resistance. Now we know that Rn input resistance is, we just find that out, 1 plus beta into what were the two resistances in the emitter branch? The two resistances were Re plus RL. Okay, so Re plus RL. So we are going to put those resistances over here. RL plus Re multiplied by Rn, 1 plus beta, Re plus RL over Re plus RL, 1 plus beta, plus R signal resistance. So Re RL will be cancelled out, and what we are left with is 1 plus beta times RL divided by Re plus RL, 1 plus beta plus signal resistance. So this is the value of the overall voltage gain that we will get for our common collector configuration. Okay, great. So let's do one example before we wrap up this lecture. All right, so let's look at this example in detail now. This is our example. In this example, what we want to do is we have a common collector configuration. We want to design an we want to design an emitter follower, right? So that this circuit is known as emitter follower because it has a voltage, open circuit voltage gain of 1. Right, so we wanted this to develop into a buffer amplifier, and this is a circuit that is given over here. So let's start with the first part of this question. We wanna specify the required bias current, right? So we want to find out the value of emitter current and the minimum value of beta, and the minimum value of beta that we should have for this circuit, right? And if we look at this circuit, in order to make sure that we have this value, the input we want to find out what is the minimum value of the beta and the emitter current that we should have in order to make sure that these are the resistances that we are connecting, right? Anyways, externally. So in order to design this circuit as a buffer amplifier, We want to make sure that we find out the value of the emitter current and the minimum beta to make sure that our output resistance R naught should be 10 ohms and our input resistance should be 100 kilo ohms. Okay, so we need to bias bipolar junction transistor such that R naught is 10 ohms and Rn is 100 kilo ohms. Okay, great. Now if we look at this model, so this is the equivalent model of this amplifier. It's a common collector, the configuration that we just talked about. We know that in a common collector configuration, our R naught equals Re, right? So this is what we just discussed in detail a lot. Our R naught equals Re, all right? So if our R naught equals Re, we also know that Re equals Vt, thermal voltage of air divided by the emitter current. So I know the value of R naught, which is 10 ohms. I know the value of thermal voltage, 25 millivolts, so I can find out the value of emitter current. So from this, R naught is 10 ohms. Thermal voltage is 25 millivolts divided by emitter current. If I will solve this equation, the emitter current is going to come out to be 2.5 milliamperes. Okay, so we can easily find out the value of the emitter current. Okay, so the second thing that we need to find out is the minimum value of beta. All right. Sorry. Okay, so let's find out the minimum value of beta here. All right. All right, so in order to find out the minimum value of beta, we are going to use this input resistance equation. We know that our input resistance equals 1 plus beta, and in that configuration, it is equals to Re plus RL. So our input resistance, looking back at the circuit, is 100 kilo ohms. So it should be 100 kilo ohms equals 1 plus beta, Re, resistance Re equals 10 ohms, and RL is 1 kilo ohms, right? So now our Re is 0.01 kilo ohms plus RL is 1 kilo ohms. So we can find out the value of beta after solving this thing, and the value of the beta that is going to come out to be 98. Right. So this is the minimum beta that we must have for the required BJT, right? However, we can use the higher value of beta, right? Because we know that beta represents the common emitter current gain. So using a higher value of the beta is desirable, so we can also use a higher value of the beta. But the important thing over here is that in order to make sure that our input and the output resistances were the same values that were given, the minimum value of the beta that is needed is 98. All right, now let's solve the second part of this problem, which is determine the maximum allowed value of the Vsig if V pi is to be limited by 5 millivolts in order to obtain reasonably linear operation. All right. Now, in order to do that, so what we are interested in finding out what is the allowable V signal value such that our V pi should be equals to 5 millivolts, and I guess we already know the value of RL. I thought it was provided in the question. Okay. All right, now we wanted to find out what is the allowable value of the voltage swings. If you remember, your overall voltage gain was V naught over V sig, right? So in order to determine the value of the V signal that is allowed, you can find out the value of the GV. So let's first find out this value of the overall voltage gain. Now, so the one thing that I am going to do is I'm going to use the formula that we derived earlier in the common emitter configuration. So GV equals 1 plus beta RL over 1 plus beta RE plus 1 plus beta RL plus R signal resistance. So we know that over here we can assume our beta value to be 100, right? So the minimum beta that was required for this operation was 98, but you can use a higher value of the beta as well. So beta, if we will assume the beta value to be 100, so it will be 101 multiplied by the load resistance. Load resistance is 1 kilo ohms. So you're going to get 1 kilo ohms divided by 101. The resistance RE is 10 ohms, 101, 1 kilo ohms plus, what is the signal resistance? Signal resistance is 100K. Oh, okay. 100K. So if you're going to solve this equation, the value of the overall voltage gain that you're going to find out is 0.5. Okay. So value of the overall voltage gain that we will obtain is 0.5. So, right, so this means that, for example, if we have V signal to be 200 millivolts, suppose that your V signal is 200 millivolts, right? So we know that GV equals V naught over V sig. So this means that if for a value of 0.5, if my signal voltage is 200 millivolts, my output voltage will be equals to half of it, 100 millivolts. Okay. Right now, this 100 millivolts, this V naught will appear across RL, which is 1 kilo ohms, right? So this V naught will be equal, will appear across this RL, and this will be equals to 100 millivolts if our signal voltage is going to be 200 millivolts. Okay, so our signal across the, base to emitter junction in this case will be equals to V pi, which will be equals to V naught over RL multiplied by RE. So we can put on these values here. Our V naught here is, for example, 100 millivolts over RL is 1 kilo ohms, let's say 1000 ohms, into RE resistance is 10 ohms. So this 10, this 10, this 100, this 100, it comes out to be 1 millivolts. So this means that this signal across the base to emitter junction, we can represent that as a V pi. So this V pi will be equals to 1 millivolt when my output voltage will be equals to 100 millivolts and my signal voltage will be equals to 200 millivolts. So if I can find out the ratio of, so one other thing that I can do is I can find out this ratio of the V sig to VI. So I can find out this ratio. V signal to V pi is 200 millivolts divided by 1 millivolt. So the ratio is 200. So if I know in this example, what we want to do is we had a 5 millivolt value given and we wanted to find out the value of the V sig. The ratio comes out to be 200. So what I'm going to do is, if I have to find out the new value of the V signal, it should be 200 multiplied by V pi, which is 200 multiplied by 5 millivolts. It will come out to be 1 volt. So this is the value of the signal voltage that we will that we can find out. Okay, and I think this question is slightly cut up. There is one more part of this question before we wrap up this lecture, and that part of the question is, so just give me 1 second, I'm trying to Okay, so yeah, so what will happen with V signal equals 200 millivolts? We want to determine voltage, determine signal at output if load resistance is changed from 2 kilo ohms to 0.5 kilo ohms. All right, so that's the third part of this question. Sorry, this was missing from the statement, from this picture while scanning. All right, so the third part is assume that our V signal now is 200 millivolts and we want to determine the signal at the output. If, for example, when our load resistance is 2 kilo ohms, what will be the change in the signal at the output if our load resistance will be changed from 2 kilo ohms to 0.5 kilo ohms? Okay, great. So now we are going to do that. So in order to do this thing, so the first thing that we want to do is, before doing this thing, is we have to find out, we are going to kind of simplify the circuit and find out the Thevenin equivalent of the circuit. Okay, so what we are interested in the C part is, we wanted to find out the value of the V naught. When load resistance is changed from 2 kilo ohms to 0.5 kilo ohms and our V signal equals 200 millivolts. Okay, so let's make a Thevenin equivalent. Let's make a Thevenin equivalent at the output. So Thevenin equivalent at the output will be equals to, so this is our V signal, this is the resistance RE, and this is the voltage V naught. And if I will make this resistance circuit over here, and then this will be over here, and this will be R out. Okay, this is RE. So our signal resistance, because of the signal reflection rule that we discussed earlier, is going to be now R sig over beta plus 1. And similarly over here, it is going to be, again, resistance reflection, R sig over beta plus 1. All right. So considering that this is a common collector, so our voltage gain is going to be 1, using this as a emitter follower. So let's find out our R naught. So our R naught will come out to be equals to RE plus R signal, right? So our equivalent, Thevenin equivalent resistance of the circuit will be RE plus R signal over beta plus 1. So this will be the output resistance. So the first thing that we want to do is we want to find out the value of R out. R out equals, again, RE in plus R sig over beta plus 1. So the value of RE is 10 ohms plus signal resistance is 100 kilo ohms divided by beta is 100, so 101. So if you will solve for this thing, our R out will come out to be 1 kilo ohms. So our resistance, output resistance, will be looking over here as a Thevenin equivalent resistance. R out will be equals to 1 kilo ohms. Okay. So let's find out the value of the V naught. So our value of the V naught now will be equals to the signal resistance multiplied by voltage divider rule, RL plus R out. Right, considering if I will simplify the circuit, so assume that the circuit is there. This is the load resistance here, right? And this is the resistance R out for the Thevenin equivalent. This is the signal resistance, and this is the resistance, signal resistance, and this is a signal voltage. So your V signal will be equals to V naught here, RL over RL plus R out. So our V naught would be equals to 200 millivolts multiplied by the load resistance 2 kilo ohms divided by 2 kilo ohms plus R out would be 1 kilo ohm. So it would be 200 millivolts 2 divided by 3. So the answer will come out to be 133.3 millivolts. All right. So similarly, this is for RL 2K. Now RL would be, when RL would be 0.5 k ohms, V naught will be equals to 200 millivolts, 0.5 k, 0.5 k plus 1 k, 200 milli divided by 0.5 divided by 1.5. So the answer that is going to come out to be 66.7 millivolts. Okay, very great. All right. So this is how we can solve this common collector circuit, and this is the last example that we are going to do. Here is the overall summary of all of these amplifiers, and this is kind of a very good summary slide because it gives you all the input, all the important formulas for major important parts of this amplifier. I've told you more so many times there are 5 components of it, right? So this is input resistance, output resistance, open circuit voltage gain, the voltage gain of an amplifier, and the overall voltage gain, and all of these formulas are given. So I hope that with this kind of a summary slide, you can solve most of the questions why the formulas are given. Okay, so this is the last example that we are going to do. And with that, I think here we are going to end up our course today. This is the final lecture for the course. There are so many other things in the course that I wanted to discuss in more detail related to BJT amplifiers and the MOS amplifiers. Yeah, but due to time constraints, we were not able to finish everything, but I hope that this has given you most of the important relevant information that you need to solve or to develop or to design these amplifier circuits. And again, our kind of concluding remarks for the course: electronic devices. This is a kind of a very important course. I guess everybody says that, sorry. But still, at the same time, right? So this discusses important concepts like transistors, operational amplifiers. So the earlier part of the first section of the course, where you discuss diodes, PN junctions, very important components, op amps, right? Very important components. And then the second part of the course is where we talked about MOS FETs, enhancement, depletion MOS FETs. We developed bipolar junction transistors. We saw that how we can use them in the amplifiers. Very important components, and try to understand, try to delve more deeper into the basics voltage transfer characteristics, overall operation of these transistors. This is very crucially important when you will move to the next courses like digital electronics or physical electronics. Some of these fundamentals will be very important in order to design these microprocessor circuits, memory units. We very briefly touched upon this, how we can use as a switch the fundamental thing in any microprocessor unit, right? So we discussed very briefly kind of how we can use a MOS FET as a switch or a BJT as a switch. BJT as a switch can be used in between saturation and cutoff. And in a MOS FET, we can use this in the cutoff and triode region, right? So, so anyways, wrapping this up. Yeah, so very important course. I hope you have learned a lot. My focus was to give you a lot of concepts. We ended up talking more about the concepts. I also incorporated some of these examples and the problems so that would help understand the concepts. And of course, You have to do the exams, and sometimes only the circuits come there. um, but yeah, anyways, overall I hope that this would have been a useful course for all of you. Okay, and I wish I would have been in person, but I guess this is the second best asynchronous thing. So anyways, thank you so much, and I wish you all the best. Your final exam will be announced soon, and I wish you all the best in the final exam for this course and all the other courses. So best of luck, stay safe, healthy, and have fun. Bye bye. Thank you.